The sun is a vital part of a plant's existence, and that includes the majority of life forms, humans and plants included. A lot of people confuse it for a planet, but it's actually a star, a yellow dwarf in the center of our solar system that could fit 1.3 million Earths inside its sphere. My topic today is about the mechanism of the sun, and how does it work? I mean, just how does it get the energy necessary to sustain both its existence, as well as providing both light and heat to the Earth? Well, it doesn't use the typical energy-producing methods, like burning a source of fuel, coal as an example, just like we're doing here. If that was the case, then it would have burned out after only 5,000 or 6,000 years. The sun instead uses a process that's not yet attainable with current science. That process is the nuclear fusion, which starts in the core of the sun and is able to produce massive amounts of energy. And this fusion began when a nebula collapsed under the force of its own gravity, starting the fusion in this process. In the core of the sun, the heat reaches more than 50 million degrees Celsius. There, the hydrogen atoms get compressed and fused together. This is nuclear fusion. How does it happen? Well, the hydrogen atoms fuse together into helium, releasing energy in this process. But it doesn't happen in a single reaction. Instead, it passes by multiple steps.
So protons combine to form a deuterium atom, a positron, and a neutrino. Then, a proton and a deuterium atom combine to form a helium-3 atom and a gamma ray. After that, two helium-3 atoms combine to form a helium-4 atom and two protons.
Two protons bounce off each other because of their positive charge, and here where does the sun's heat plays a role. Due to very high temperature, the protons move so fast that they sometimes can't avoid colliding with each other. And that happens when hydrogen's speed gets accelerated enough that the nuclei can overcome the electrostatic repulsion of the charges. That basically means that the high temperature gives the hydrogen atoms enough energy to overwhelm the electrical repulsion force between the protons. But that's not enough. The fusion would require a heat 6 times more than that of the core. So, in addition to the temperature, high pressure is also a requirement for the fusion. So the sun uses its mass and powerful gravity to basically squeeze hydrogen atoms together in its core. The hydrogen in these conditions is not gas, but it's actually plasma. These reactions account for 85% of the sun's energy. The remaining 15% comes from other reactions that involve other elements, like when a helium-3 atom and a helium-4 atom combine to form a beryllium-7 and a gamma ray. The hydrogen atoms that started this chain of reactions are bigger than the resulting helium-4 atoms. Hence, the loss of mass that gets compressed into energy, which is described by Einstein's famous equation E equals mc squared. That energy is emitted in different forms of light: UV, X-rays, IR, radio waves, or even visible light. During this constant process, the sun loses 4.3 billion kilograms of its mass every second.